Hey everyone, welcome back to another episode. I'm Nova. So Alloy, I've got a question for you. Have you ever tried to run a 72 billion parameter model on your laptop? Yeah, exactly. I mean, we're talking about a model that needs somewhere around 150 gigabytes of VRAM to run properly. That's more memory than most people's entire computers have. Let alone a laptop that you might take to a coffee shop. Right. So here's where things get interesting. What if I told you that you could take two of those beautiful Mac Studios sitting on your desk, the ones with the M3 Ultra chips, and actually run a 72B model across both of them? Split the layers between the machines, distribute the computational load, and get something actually usable? It sounds like magic, but it's actually a real thing, and it's called exo-labs. And today, we're going to dig into everything you need to know about building your own distributed AI cluster using Apple Silicon. This is going to be a deep one, so buckle up. Great question. And the answer is really simple. Models keep getting bigger, but hardware has hard limits. I mean, look at where we were even 2 years ago. Models were measured in billions of parameters, and now we're casually talking about 70, 80, even 100 billion parameter models. It's just been this relentless march toward bigger and better. And hardware hasn't kept pace at the same rate. Exactly. You think you've got headroom, and then you actually try to run one of these models and realize you're swapping to disk and your inference speed drops to like 1 token per minute. It's painful. Exactly. So distributed inference, spreading the model across multiple machines, that's the way forward. And exo-labs is the project that's making that actually possible on Apple Silicon, in a relatively accessible way. It's peer-to-peer, it's designed specifically for our Macs, and it's open source. That's the revolution here. Democratization. Making distributed inference accessible to regular developers and researchers who don't have access to enterprise clusters. That's what we're here to talk about. Let's dive in. Segment 2, what is exo-labs? So Alloy, let's get into the nuts and bolts. What is exo-labs, exactly? That's right. It's an open source project, and here's the important part, it's actively maintained. As of February 25, 2026, they're at version 1.0.68. That's recent. We're recording this in early 2026, and the project is clearly being actively developed. That's a good sign. The commit history looks healthy, the issues are being responded to, and new versions are dropping regularly. That's exactly what you want to see. The core idea is that exo-labs shards model layers across multiple machines. So instead of trying to fit the entire 72B model onto one Mac, you split the layers. Machine 1 handles layers 1 through 36, Machine 2 handles layers 37 through 72, and they communicate with each other during inference. Exactly. Each machine is responsible for a contiguous range of layers. When you prompt the model, the input goes to the first machine, which processes its layers and passes the output to the second machine, which processes its layers, and so on. It's like an assembly line. Exactly. And it leverages MLX Distributed, which is Apple's machine learning framework for Apple Silicon. MLX itself is already incredibly optimized for the M-series chips. Apple's done amazing work there, and the distributed version lets you spread computations across multiple machines. exo-labs sits on top of that and handles all the coordination. And Apple has been investing heavily in MLX and making it more capable. So exo-labs benefits from all of that work. It's a virtuous cycle. The results are pretty compelling. According to their benchmarks, you can get roughly 1.8 times the speedup with just 2 nodes. So instead of waiting forever for your 72B model to generate a response, you're getting close to double the throughput. That's the difference between something being usable and something being painfully slow. In theory, yes. Though there are practical limits around network latency and the overhead of transferring activations between machines. But for 2 to 4 nodes, which is what most people would realistically set up, the speedup is significant. And as the software improves and we get better networking options, those numbers will only get better. Good question. exo-labs works with any model that MLX supports, which is a growing list. We're talking about the Llama family, Qwen, Mistral, DeepSeek, all the major open weight models that people actually want to use. And the other piece that's really nice is the peer discovery. I know we touched on this briefly earlier, but let's go deeper. That's the beautiful part, no. exo-labs uses MDNS for peer discovery. MDNS is multicast DNS, and what that means in practical terms is that if your machines are on the same local network, they find each other automatically. You don't need to mess with IP addresses or network configuration. It's genuinely plug and play. Essentially, yes. The whole discovery process is automatic. Both machines run the exo-labs process, they broadcast their presence via MDNS, they see each other, and they form a cluster. It's that simple. This is definitely a different era. Now, for the best performance, you definitely want a wired connection. We're talking Thunderbolt direct connections for the fastest internode communication. But for getting started, MDNS discovery on a local network works out of the box. Exactly. That's a great way to get started. Run it over Wi-Fi, verify everything works, and then invest in the Thunderbolt cables and direct connections for the real deal. That's a really important distinction, and it's where things get nuanced. Let's talk about that. Segment 3, Source versus EXO.app. The app is definitely simpler. You download it, you install it, you open it, and everything just works. There's a GUI, you click some buttons, and you're off to the races. For someone who just wants to try it out and see what distributed inference looks like, the app is perfect. It's the low-friction entry point. The downside is transparency and control. When you run the app, the logs are hidden. You can't easily see what's going on under the hood. There are no recovery scripts built in. And the app requires a GUI. If you're running headless servers, you're out of luck. Absolutely. And that's where running from source comes in. You clone the repository, git clone github.com/exo-explore/exo, and then you run it with UV run exo. That gives you full visibility into everything that's happening. There's one critical advantage that I want to highlight: access to the RDMA recovery script. If you're using RDMA for your internode communication, and we'll get into what RDMA is in the next segment, sometimes things go wrong. Connections drop, and you need a way to recover. The script at tmp set_rudmer_network_config.sure is your lifeline there. We'll get to that in detail in the next segment. But yes, exactly. And the point is, that recovery script is only available when you run from source. The app version doesn't expose it. You can't access it through the GUI. Essentially, yes. You'd have to fall back to the source version to debug and recover. So from the start, if you know you're going to use RDMA, just start with source. Exactly. And here's another detail. In version 1.0.68, they added logs at tilde.exo_logs. So when you're running from source, you can actually see what's happening. You can debug issues. You can monitor performance. That's huge for troubleshooting. 100%. If you're setting this up in a production environment or even just for serious experimentation, running from source is the move. The app is great for getting your feet wet, but for any reliability-focused setup, you want full control. That's a good point. And since the project is actively maintained with frequent releases, being on source means you get access to the latest fixes and features as soon as they're available. Now, let's talk about the gnarly stuff. The part where things can actually go wrong. Because exo-labs is impressive, but it's not magic. There's some real complexity underneath, especially when it comes to RDMA. And that's where a lot of people get tripped up. Segment 4, RDMA Deep Dive. RDMA stands for Remote Direct Memory Access. And what it does is pretty remarkable. Normally, when two computers communicate over a network, the data has to go through the CPU. The CPU has to read the data from memory, send it out over the network, and then the receiving CPU has to process it. It's fine for most use cases, but when you're transferring large amounts of data repeatedly like you do in distributed inference, that CPU overhead adds up. Exactly. And that bottleneck becomes a real problem when you're trying to move gigabytes of activation data per second. Precisely. RDMA lets the network card directly read from and write to memory, without involving the CPU at all. That means dramatically lower latency and dramatically higher throughput. For our use case, where we're constantly passing activations and layer outputs between machines, RDMA is a game changer. That's exactly what it is. It's a direct memory channel. And for distributed inference, that directness is crucial. Every microsecond matters when you're pipelining between nodes. There are catches. Several of them. First, you need the right hardware. For Mac Studios, you need Thunderbolt 5 cables. Not Thunderbolt 4. TB4 won't work for RDMA on Mac Studio. You need TB5. You might be able to, but it won't work for RDMA. And there's a specific reason for this. Thunderbolt 5 has higher bandwidth and lower latency than Thunderbolt 4, which matters for RDMA. The technology simply isn't supported on TB4. Exactly. And here's a weird one. You cannot use the Thunderbolt 5 port that's adjacent to the Ethernet port on the Mac Studio. For some reason, that specific port doesn't support RDMA. You have to use the other TB5 ports. It'll be in the documentation eventually, but yeah, that's the kind of thing that trips people up. You really need to pay attention to which port you're using. Now, here's the big one. The number one cause of RDMA failures: macOS versions must match exactly across both machines. Exactly. If one machine is running macOS 15.2 and the other is running 15.3, RDMA will fail. Not might fail, will fail. The versions have to be identical. And it's not just about being careful, it's about being deliberate. You need to make sure both machines are on the exact same macOS version before you start your exo-labs cluster. Once you have it working, you probably want to delay updates until you've tested compatibility. You do. And that might be a deal breaker for some people. But if you want the performance, that's the price of admission. There are several known failure modes. GPU lock from MLX_metal_fast_SYNCH. This is an environment variable that can cause issues when both machines are trying to synchronize their GPUs. Sometimes nodes get stuck in a loading state, which means they're waiting for other nodes to connect, but something went wrong in the handshake. And the Thunderbolt bridge, which is what handles the direct connection between machines, can cycle on and off unexpectedly. This is cutting-edge stuff. It's not as battle-tested as running inference on a single machine. You're introducing a lot of new variables. Right now, no. If your RDMA connection drops, you need manual intervention. You have to restart the cluster, check your cables, verify your macOS versions, and try again. There's no built-in auto-recovery mechanism. Absolutely. You need to be comfortable troubleshooting network issues, checking logs, and doing some manual recovery. This isn't for someone who wants something that just works out of the box without any maintenance. But here's the good news. The exo-labs team has been actively fixing these issues. Let's look at the recent version history. Version 1.0.64 introduced IP-less RDMA discovery, which was a huge improvement. Version 1.0.66 fixed the loading state issue. Nodes were getting stuck and couldn't recover, and that was addressed. And version 1.0.68, the current version, addressed the GPU lock issue. They're moving fast. Version 1.0.68 came out on February 25, 2026, so this is very recent development. The project is alive and improving. But you need to go in with your eyes open. This is cutting-edge technology. It works, it's impressive, but it's not as polished as a mainstream tool that has been around for years. That's the right way to frame it. And honestly, for many users, just starting with a basic network setup and skipping RDMA might be the better move initially. Get everything working, verify your cluster is stable, and then upgrade to RDMA once you have a baseline. Exactly. Alright. So that's the first half of our deep dive on exo-labs. We've covered why distributed inference matters, what exo-labs is and how it works, the differences between the app and source, and the nitty-gritty of RDMA. Exactly. So if you're thinking about building your own distributed AI cluster, stay tuned. There's a lot more to come. Catch you next time. Building a distributed AI cluster with exo-labs, Part 2. Segment 5 Model Selection Guide. Okay, so we've got an exo installed, we've got our machines talking to each other, we built a Thunderbolt bridge. Now the question everyone actually cares about, what models can we actually run on this thing? Like, I have 2 powerful Macs sitting here, I want to use them. What can I actually throw at this cluster? Let's break it down for the folks at home. Your setup is an M3 Ultra with 96 GB and an M4 Max with 64 GB. That's 160 GB of unified memory total when you combine them. But here's the critical constraint that we've learned the hard way through testing. Models requiring over about 100 GB total have been unstable. The connection between the machines starts to choke, you get weird inference glitches, and honestly it just becomes a massive headache. And then if you quantize down to 8-bit, that's 1 byte per parameter, so that same 70 billion parameter model only needs about 70 GB. Cut it in half. And at 4-bit, which is what a lot of people use for running larger models on limited hardware, you're looking at just 0.5 bytes per parameter, so about 35 GB for that same 70 billion parameter model. First up, Qwen 2.5:72B at 4-bit quantization. That's about 40 GB. Your M3 Ultra handles that with room to spare. You've got almost 60 GB of memory left for context, for the running application, for everything else your Mac needs to do. This is a great daily driver. DeepSeek R1 at 32B with 8-bit quantization is around 20 GB. That's a fast reasoning model, really snappy, great if you need quick thinking without waiting around. The 32B size is interesting because it's small enough to run fast but still smart enough to be useful. It's that middle ground that a lot of people overlook. Now here's where distributed exo actually starts to shine. This is cluster territory. These are models that need both machines to run, that would choke on a single Mac, but become viable when you combine that 160 GB of unified memory. Another interesting one is Qwen 3-235B Mo at 4-bit. That's around 120 GB. Now, Mo stands for Mixture of Experts, and these models are really efficient because they only activate subsets of parameters for each token. It's not actually loading 235 billion parameters into memory, it's loading the active experts, which is much smaller. That's the magic of Mo architecture. It's worth trying across your cluster, and if anyone has the hardware to try this, we're really curious how it performs. And now let's talk about what to avoid. This is important, because we see people try this all the time and then wonder why their cluster keeps crashing. Non-MoE models over 100B parameters are also going to give you trouble. The memory requirements spiral out of control, and the connection overhead between your 2 machines becomes a bottleneck rather than a benefit. You're adding latency without getting any throughput improvement. It's like trying to coordinate 2 people to move a feather, the coordination costs more than the actual work. Pick the right model for your hardware, and exo will sing. Push too hard, and you'll be debugging connection issues at midnight. We've all been there. Well, maybe not all of us, but definitely me. Don't be me. Segment 6 Watchdog and Demonizing. Right. You want it running in the background, automatically, surviving restarts, that kind of thing. You want exo to just be there when you need it, like a server, like infrastructure. But here's the thing, exo has no built-in service manager. That's a gap in the current design. The naive approach is the nohup command. You've probably seen this before, maybe in some old blog post or sysadmin guide. You run nohup uv run exo.exo.log2 and 1 and init backgrounds the process. The nohup keeps it alive if you disconnect from the SSH session or close the terminal, the ampersand runs it in the background, and you're redirecting output to a log file. The better approach on macOS is LaunchTool. This is the system-level service management that Apple has had forever. You create a plist file, basically a configuration file, that tells the system how to run exo, and more importantly, you can configure it to auto-restart on failure. If exo dies, LaunchTool catches it and brings it back up automatically. There's one environment variable you absolutely need to know about, exo_libp2p_ namespace. Set this to your cluster name, Something like ExoCluster NYC or MyHomara Cluster or whatever makes sense for you. This is critical. Also, log rotation. This was added in version 1.0.68, and it's one of those features that you don't appreciate until you've been burned by the alternative. Before that, your log files could grow without bound until you ran out of disk space. Imagine waking up one day and your Mac won't boot because some log file ate your entire hard drive. It happens. Now Exo handles rotation automatically. You set a max size or a max age, and it cycles through logs. Huge quality of life improvement. The whole thing should be automatic if you've set it up right. You wake up in the morning, your cluster is still running, everybody's happy, tokens are flowing. It's beautiful. It's what infrastructure should feel like. Alright, let's get real. We've spent a lot of time talking about how to set this up, the math, the configurations, the reliability engineering. But what's the actual verdict? Is Exo worth it? Should people actually do this? But they're working on it. The team is actively addressing these issues. This isn't an abandoned project. People are contributing, issues are being filed, pull requests are being merged. But if you're going into this expecting a polished, turnkey experience like you'd get from a commercial product, you're going to be disappointed. This is open source. This is early-stage technology. You have to meet it where it is. And seriously, don't cheap out on your Thunderbolt cable. This is not the place to save $20. Get a good quality TB5 cable from a reputable brand. The cheap ones introduce latency and instability, and you'll be chasing problems that are really just bad hardware. We cannot stress this enough. The cable is the foundation of your cluster. Don't build your house on sand. It's the future. The machines are talking to each other, dividing the work, producing results faster than either one could alone. You're running a distributed system in your home. That's genuinely incredible when you stop and think about it. Will it be perfect? Probably not. There will still be hiccups, there will still be moments where you need to kick things, there will still be issues that require digging into logs and debugging. But it'll be good enough that you can actually get work done. And as the software matures, it'll only get better. That's fair. That's honest. We could sit here and pretend it's perfect, but it's not. But what it is exciting. And for the right person, it's exactly what they're looking for. Segment 8 sign off. Okay, let's wrap this up. We've covered a lot of ground in this second half. What's the key takeaway from everything we've talked about in segments 5 through 8? Demonize properly. Don't just no-hop it and hope for the best. Use LaunchTool, set up auto restart, configure your namespace so you're isolated from other users on your network. Treat it like infrastructure, because that's what it is. And be patient. Exo is actively developing. The rough edges will get smoother over time. The documentation will improve. The defaults will get better. But right now, you have to be willing to put in a little work to get the rewards. That's the deal. That's the bargain. It really is a lot. And if you build this cluster, if you get it running, if you watch those tokens flow between your machines, remember what you're doing. You're running a distributed AI cluster in your home. That's genuinely incredible. That's something that would have required a server room 5 years ago. Also, different model architectures have different memory footprints beyond just the parameter count. Some models use more memory for attention computations. Some have more overhead in their implementation. The math we talked about is a good starting point, but always test. Always run the model and watch your memory usage before you commit to it as a daily driver. Another thing about the demonization. One more tip. Watch your system logs. Not just the Exo logs, but the system logs too. Sometimes the issue isn't Exo itself, it's something at the OS level. Network configuration changes, power management issues, thermal throttling. All of those can affect your cluster stability. The more visibility you have, the easier it is to diagnose problems. That's the spirit. That's what makes this whole thing worthwhile. We're all building together. We're all figuring this out together. And that's really cool. That's huge. That's genuinely huge. In a world where more and more of our computing moves to the cloud, being able to run sophisticated AI models locally, on your own hardware, is a form of digital autonomy. It's powerful. And it's something worth pursuing, even if it's harder than just using an API. Exactly. You're future-proofing yourself. You're learning the skills, understanding the architecture, getting comfortable with the challenges. By the time this becomes mainstream, you'll already be an expert. You'll already know how everything works under the hood. It really is. The machines are talking to each other now, and that's not just an ending line. That's what's actually happening. You're running a distributed system. You're doing distributed computing. That's computer science at a pretty fundamental level, and you're doing it in your home. See you next time.